Going over the review sheet today, we finished up with problem number 44, I believe, yesterday. So we'll move on and look at number 45. Problem number 45, 7 to the x is equal to 3. Now, for this one here, we do need to get the x out of the exponent, and we're going to have to use logarithms. We cannot get the bases to be the same because there is no number that we can rewrite to get 7. 7's prime. So what we're going to do is apply a logarithm to both sides to get the variable out of the exponent. And the logarithm that we're going to apply, the base of it, is going to match the base of which one the variable is in the exponent of. So we have 7 to the x. I'm going to apply log base 7 to both sides. So on the left-hand side, we have log base 7 of 7 to the x is equal to log base 7 of 3. And according to our exponent properties, our power properties of logarithms, the exponent will move to the front, telling us that we have x times log base 7 of 7, which is equal to log base 7 of 3. Now, log base 7 of 7, if we wanted to calculate it, we can go grab the graphing calculator, go math, log base 7 of 7 is 1. So it tells us that this here is going to simplify to 1, giving us 1 times x, which is just x, is equal to log base 7 of 3. Now at this point here, we need to solve for x. We need to get x by itself. Well, it is, so that there is our answer. Now, if we wanted to get the decimal approximation, we could grab the graphing calculator, go math, log base 7 of 3, and we get 0.56457 or 0.565. And again, for this here, I would take both of these here. Definitely give me the log base 7 to 3. But if you also give me the decimal answer, that is fine as well. Questions on how we got to this here? We're ready for the next one. Let's look at 46. Now, the first two that we did, 40 and 41, we could try to get the bases to be the same, but there's no way to rewrite 11 and 38 so that they are both the same base. And that's fine. We're going to do the exact same thing we did on the last one, and since the base that has the variable in the exponent is not e, we're going to use log. We're going to use log. We're going to apply a log to both sides specifically. And what's going to be nice for us is if we apply log base 11 to both sides. And the reason we're applying a log is to get this exponent, the variable in the exponent, out of the exponent. Because according to our power properties, we can move the 6x plus 2 out in front of the log, turning the left-hand side, instead of having it 11 to the 6x plus 2, we now have 6x plus 2 times log base 11 of 11. And the right-hand side is just going to be log base 11 of 38. Questions on this so far? Now, log base 11 of 11, just like log base 7 of 7, is going to simplify to 1. So we have 6x plus 2 times 1 which is just 6x plus 2. Now, unlike the last one, x is not by itself, so we still need to solve and get x by itself. And the first thing we can do is what? We can subtract 2 from both sides. Because on the left-hand side, our positive 2 minus 2 would be 0. So we're just left with 6x. On the right-hand side, we're going to get log base 11 of 38 minus 2. We cannot subtract the 38, and 2, we cannot combine those because they are not like terms. And last but not least, to get x by itself, we're going to divide both sides by 6. Telling us that x is equal to log base 11 of 38 minus 2 all over 6. X is by itself, so this here is solved. And because x started off in an exponent, we don't have any restrictions. There are no values of x that we cannot have that are not real numbers. Now, at this point here, if we wanted to, we can plug it in the calculator, go alpha y equals enter to get our starting fraction. Math. Log base 11 of 38 minus 2 over 6. So it tells us that x is approximately negative 0.081. Questions on this here? Questions on any of this so far? Questions? Before we move on to the next one, let's look at 47. Natural log of 3x plus 2 is equal to the natural log of 4x minus 5. Again, this is our one-to-one property. We have logs on both sides. We have one log equal to another log. And the only way this is true is if what's inside the logarithms are also equal. So the only way the natural log of 3x plus 2 is equal to the natural log of 4x minus 5 is if 3x plus 2 is equal to 4x minus 5. Now, we do not have any x squared terms. We do not have variables to exponents bigger than 1. We just need to get x's on one side, numbers on the other. Doesn't matter what we do first. I'm going to subtract 3x from both sides, telling me that 2 is equal to x minus 5. Then we can add 5 to both sides, telling us x is equal to 7. And that's it. Questions on this here? And yes, if we wanted to, we could go back and check it and plug these in. Natural log of 3x plus 2. So if I checked, it'd be the natural log of 3 times 7 plus 2. And that would give us this here. And I could plug it into the other side. The natural log of 4 times 7 minus 5 is also the exact same number. Even though they're both irrational numbers, because they have the same value, they are equal. So therefore, x is indeed 7. Questions on 46 or 47? Yes. Questions on 48 or 49? Okay. Which one? 48. Log of 7x plus 3 is equal to log of 38. Since these are the exact same logs, the only way they can be equal is if what's inside each one of them is equal. So we're saying that 7x plus 3 has to equal 38. Now, since we don't have an x squared term, x cubed, these higher degree polynomial expressions, we just need to get x by itself. So the first thing I would do is subtract 3 from both sides, telling me that 7x is equal to 35. Divide both sides by 7, telling us x is equal to 5. Any other questions on 48? Let's look at 50. Log base 2 of x squared minus x minus 6 is equal to log base 2 of negative x. Now, just like the last two, because our logs are the exact same, they're log base 2's, the only way they can be equal is if what's inside each equation is also equal. So what we're saying is x squared minus x minus 6 is equal to negative x. Now this one, unlike the last few, we do have an x squared term. We do have this quadratic term. So we need to get this equation equal to 0. And the first thing I would do is add x to both sides, telling me that x squared, well, negative x plus x is 0. So really we're left with x squared minus 6 is equal to 0. Now this is actually kind of nice, because if we had that middle term, we had a term with just x, we'd have to go about factoring, quadratic formula, these methods. But because we do not have a middle term, we can use the square root method. We're going to get x squared by itself. And to do that, we're just going to add 6 to both sides, telling me that x squared is equal to 6. To get rid of the x squared, we're going to have to take the square root. Square root of x squared is just x. Square root of 6 does not simplify nicely. It is not a perfect square or have perfect square factors. So we just leave it as the square root of 6. And whenever we take the square root of both sides, we do have to put the plus or minus. So really we have two separate answers here. We have x is equal to square root of 6 and x is equal to negative square root of 6. We do have two separate answers, and we will need to check both of them to make sure that they work. Because if we check the positive square root of 6, we have log base 2 of the square root of 6 squared minus the square root of 6 minus 6 is equal to log base 2 of negative square root of 6. So all I've done is gone back through and replaced every x with the square root of 6. Now on the left-hand side, we'd have log base 2, while our square root of 6 squared is going to be 6. Minus the square root of 6 minus 6. Well, our 6 and negative 6 would be 0, leaving us with log base 2 of negative square root of 6. On the right-hand side, our negative square root of 6 is just going to become negative square root of 6. So once we finish simplifying everything inside the radical down before taking the logarithmic, or log base 2 of each side, we get log base 2 of negative square root of 6 is equal to log base 2 of negative square root of 6. Is this a true statement? Is this true? Is log base 2 of negative square root of 6 equal to log base 2 of negative square root of 6? And the answer is no. I cannot take a logarithm of a negative number. Even though both sides are the exact same expression, it doesn't matter because I cannot take log of a negative. Neither one of these have a value, so they can't be equal to each other. So that's telling us that positive square root of 6 does not work. This is one of the first times where x being a positive value did not work in the original problem. I'm going to erase this here and I'm going to check again. And this time I'm going to check with the negative case. We're going to have log base 2 of negative square root of 6 squared minus negative square root of 6 minus 6 is equal to log base 2 of negative square root of 6. Now we feel like if the positive case didn't work, there's a good chance the negative case will not work either. Now negative square root of 6 squared, negative times a negative is a positive. Our square root of 6 times the square root of 6 is going to be positive 6. Our negative square root of 6, the negative and negative make a positive, giving us just the square root of 6. Our 6 minus 6 is 0, leaving us with log base 2 of the square root of 6. On the right-hand side, our negative square root of 6 is just going to become square root of 6. And log base 2 of square root of 6 is indeed equal to log base 2 of square root of 6. Since what's inside the logarithm is a positive number that is not 0 or negative, this works. So the answer for this is that x is equal to negative square root of 6. Just because x is a negative does not mean it does not work in the original context. Questions on number 50? Yeah. Okay. Let's look at problem number 51. Log base 7 of 4x plus 9 is equal to 2. So whenever we have these here, especially numbers outside the logarithms, we want one term on either side. We want the log by itself, all of our numbers on the other side. And 51 is already set up in that way. And once we get it set up this way, we're going to put both sides to the base of the logarithm. Since the logarithm's base is 7, we're going to put both sides to the base of 7. So on the left-hand side, we have 7 to the log base 7 of 4x plus 9. Well, the 7 base and log base 7 are going to simplify out, leaving us with what's inside the log, which is 4x plus 9, is equal to 7 squared. Now we're going to see if 7 squared is a nice number, which it is. It's going to be 45. We're going to consider it a nice number if it's a not irrational, non-repeating, non-terminating decimal, or the number is just not way too big. And lastly, we need to solve for x. Now, since x is not squared, we just need to get it by itself. So the first thing we can do is subtract 9 from both sides, telling us that 4x is equal to 40. Then we would divide both sides by 4, telling us x is equal to 10. Questions on number 51? if we wanted to check it, we could grab the graphing calculator, go math, log base 7 of 4 times 10 plus 9 4 times 10 plus 9, and we see that it is indeed 2. That is what we wanted the equation equal to. So x equals 10 is the correct answer. Any other questions on number 51? Let's look at problem number 52. The natural log of 6x minus 2 equals 7. We have one term on either side, so we can go on and apply the base of the logarithm as a base to both sides. Now, since we're talking about natural logs, even though the base is not written, it's understood to be e. So we're going to put both sides to the base of e. And e to the natural log is 6x minus 2. E and the natural log will simplify out, telling me that 6x minus 2 is going to equal e to the 7th power. E to the 7th, we can use the calculator to figure out what that is. And e to the 7th is an irrational number, so for the time being, we will leave it as e to the 7th power. So we get 6x minus 2 equals e to the 7th. We just need to get x by itself. So the first thing we can do is add 2 to both sides. Telling me that 6x is equal to e to the 7th plus 2. We will not add the 7 and 2 because the 7 is in an exponent and the 2 is not. Questions on this here? And lastly, to get x by itself, we're going to divide both sides by 6, telling us x is equal to e to the 7th plus 2 divided by 6. And if we wanted to see what this is, we can grab a calculator, say second e to the 7th plus 2. Well, let's put it into fractions. Second e to the 7th plus 2 all over 6 is 183.106. Any other questions on 50 through 54? Okay. 54, natural log of 6x minus 4 equals 15. Yeah. Okay. Question on 55 or 56? We're going to look at 56. Log base 2 of x plus log base 2 of x minus 2 is equal to 3. We need one log on either side. We need one log. We cannot have it written as 2. If we have two logs with the same base being added together, we can rewrite it as a single log with what's inside being multiplied. So if we do have two logarithms added together, we can rewrite it as a single log with what's inside being multiplied. And really from this point on, it's going to be the exact same as what we did on the last two. We're going to put both sides to the base of the logarithm. Now, since the logarithm's base is 2, we're going to put both sides to the base of 2. And 2 to the log base 2 will simplify out, leaving us with x times x minus 2 is equal to 2 to the third power. Now at this point here, we will have to multiply that left-hand side. We're going to have to distribute the x. X times x is x squared. X times negative 2 is negative 2x. And 2 to the third, 2 times itself 3 times will be 8. Now because we do have an x squared term, and we do have a middle term, we do need to get this equation equal to 0. So we're going to subtract 8 from both sides. Telling us that x squared minus 2x minus 8 is equal to 0. And once we get it in this form, we're going to factor it and solve. All the ones on the test will be factorable. We'll be able to factor them to find the solutions. You will not have to use the quadratic formula for any of them. So we'll have our 2 sets of parentheses with 3 spaces because there is no greatest common factor. Now we need to find the sign. Since the third term is negative, our signs are going to be opposite. One's going to be positive and one is going to be negative. Factors of x squared, the only factors are x and x. Then our factors of 8 are 1 and 8 or 2 and 4. And for us here, we're going to want to use the factors of 2 and 4. And if we want to check and make sure we got the correct factors, we'll multiply our outer and inner. X times negative 4 would be negative 4x. Positive 2 times x would be positive 2x. So negative 4x plus 2x, negative 4 plus 2 is indeed negative 2x that we wanted. Questions on this here? We have 2 things multiplied together to equal 0. So one of these, either x plus 2 is 0 or x minus 4 is equal to 0. Now for our x plus 2 to solve it, we would subtract 2, telling us x is equal to negative 2. With x minus 4, we would add 4, telling us x is equal to 4. Now, especially if we get more than one solution, we will need to check them, especially if we get these negatives. We'll need to check our answer. Back into the original problem, our log base 2 of x plus log base 2 of x minus 2 is equal to 3. So if we check negative 2, log base 2 of negative 2 plus log base 2 of negative 2 minus 2, if we fully simplify everything, we get log base 2 of negative 2 plus log base 2 of negative 4 equals 3. We cannot have a negative inside the logarithm once we finish simplifying. So it's telling us x cannot be negative 2. If we do the same thing with 4, and we simplify, we get log base 2 of 4 plus log base 2 of 2 is equal to 3. We're good there. We're mainly checking to make sure that we do not have a negative inside those logs. Incidentally, log base 2 of 4 is 2. Log base 2 of 2 is 1. And 2 plus 1 is indeed equal to 3. So the correct answer for this here is x equals 4. Questions on this here? Okay, that brings us to the last type of problems, our inequalities. We're going to do 2 with logarithms, then we're going to do 2 with exponentials. When we start off with logarithms, we do have restrictions in that what's inside the logarithm has to be greater than 0. Because if what's inside the logarithm, if the value of x makes, in this case, x minus 1 be 0 or negative, we have to throw those values out. So we're going to set what's inside the logarithm greater than 0 and then solve for x. So for 57, we're saying that x has to be greater than 1. Whatever the solution set that we get is, we cannot include values of x that are equal to 1 or less than 1. Because if we do, we have values of x that would make what's inside the log be 0 or negative. Once we have that stated, we can go about solving. Just like with our equation, since we do have one term on either side of that inequality sign, we can put both sides to the base of the logarithm. And since it's a natural log, the base is e. So we're going to put both sides to the base of e. E in the natural log will simplify out, leaving us with what's inside the log, which is x minus 1. And we're saying that the x minus 1 is greater than or equal to e to the 9th power. Just like before, e to the 9th is an irrational number, so we'll leave it as e to the 9th till the very end. Then we're going to get x by itself, and luckily for this here, the only real thing we'll have to do is add 1 to both sides, telling us x is greater than or equal to e to the 9th plus 1. Questions on how we got to this point here? Now, the last thing we have to do is check and make sure our restrictions do not come into play. We don't have to add them back in. Now, we said that our restriction, our values of x have to be greater than 1, yes? What's a value of x that would make this statement false? What's a value of x that's less, not greater than 1? Negative 1, yes? So I'm going to take that value and plug it into this here. This is negative 1 greater than or equal to e to the 9th plus 1. And if we want to check, e to the 9th plus 1 is 8,104. So is negative 1 greater than 8,000? Well, no. Because it doesn't make it a true statement, I don't have to include those restrictions. So our solution set are the values of x that are greater than or equal to e to the 9th plus 1. That's it. Questions on this here? Questions on 58? Okay. Next one we're going to look at is number 60. 5 log base 7 of 4x is greater than or equal to 160. Again, since we're starting off with logarithms, we will need to look at the restrictions, which is just telling me what's inside the logarithm has to be greater than 0. Well, what's inside our logarithm for this one here is 4x. So it's telling us that 4x has to be greater than 0, or, well, realistically, x has to be greater than 0. If x is equal to 0 or less than it, we will have, or we will be taking log of a negative number, and that does not work. Questions on how we found the restrictions for this here? Now, before we can start solving, we do need to get the logarithm by itself. Since we have this multiplication of 5 in front of it, we're going to have to divide both sides by 5 first. Now, the left-hand side is just going to become log base 7 of 4x is greater than or equal to 32. Because we did not multiply or divide by a negative, we just divided by positive 5. That inequality sign does not change. Now, since the logarithm is by itself, we're going to put both sides to the base of the logarithm. And the base of the logarithm is 7. So we're putting both sides to the base of 7. Giving us the left-hand side of 7 to the log base 7 of 4x. Well, that 7 and log base 7 will simplify out, leaving us with 4x. Telling me 4x is greater than or equal to 7 to the 32nd power. Is 7 to the 32nd power a nice number? No, that number is going to be massive. It's not irrational. It is just a very, very large number. So in this case here, we're going to leave it as 7 to the 32nd power. Now we do need to finish solving for x. So the last thing we can do is divide both sides by 4. Telling me x is greater than or equal to 7 to the 32nd all over 4. Questions on how we got here? Is 0 bigger than 7 to the 32nd over 4? No, that's going to be a massively large number, and we're just saying we got numbers bigger than it. Since the restriction does not come into play, we don't have to add it back in. Questions on number 60? Two more we're going to look at. The next one we're going to look at is 62. 3 to the 4x minus 5 is greater than 108. If the restriction had come into play, let's say I flipped it. Let's say this was the answer. X is less than or equal to 7 to the 32nd over 4. Okay, the restrictions do come into play. I throw that statement onto it. We remove those. That's it. And yeah, so $58, we would have to add the fact that negative 2 is less than x. Yep, that's all we have to do is we just have to throw that statement back onto it. 62. For this one here, the variable starts out in an exponent, yes? There are no restrictions on exponents. We can have whatever number we want in an exponent, so we do not have restrictions for these here. We have one term on either side. So the first thing we want to do is get that variable out of the exponent. So I'm going to apply a log to both sides, specifically log base 3. Because I want that left side to simplify. I want it to be written a little bit nicer. Now, part of the reason we apply a log to both sides is to get that variable out of the exponent. According to the power property, I can move that exponent out of the exponent to in front of the log, changing it from log base 3 of 3 to the 4x plus 4x minus 5 to 4x minus 5 times log base 3 of 3. Log base 3 of 3 is what? 1. Since the base and the number inside are the same, it reduces to 1. So log base 3 of 3, or 1 times 4x minus 5 is 4x minus 5. That's why we use log base 3 of log base 3, so that left-hand side would simplify to be something nicer. Last thing we got to do is get x by itself. So the first thing we can do is add 5 to both sides. Tell me that 4x is greater than log base 3 of 108 plus 5. X is still not by itself, so we're going to have to divide both sides by 4. Give myself a little more room. And when we divide both sides by 4, 4x divided by 4 is going to be just x. Is greater than log base 3 of 108 plus 5 all over 4. And that is, and for most of these here, we'll leave it as this form because inequalities get a little tricky with how they work. Because if we rounded to the third decimal place, realistically with inequalities from what I've observed, most of the rules we have for inequalities, or rounding, we kind of throw out the window. Because it is less than, we would go to the third decimal place and round down, regardless of what the fourth one is. Because of the fact that it's not that specific number, it's greater than it. So I would leave it as this here. Any other questions on any of these here? All right. Part 1 is tomorrow, and part 2 is Thursday.